Okay, welcome back Physics 30s to our next lesson. This is 1.2 and today we're going to be looking at X and Y. In Physics 20, you look a lot at vectors.
Vector!
And in case you forgot,
it's a mathematical term, a quantity represented by an arrow with both direction and magnitude.
And we described a lot of vectors like displacement and velocity, and one big topic that carries through into Physics 30 is the idea that X does not affect Y. What I mean by this is that vectors in one plane are unaffected by vectors that are 90 degrees to this plane. So this means that if we had motion going on in the y-axis or the vertical axis, that would not be affected by motion going in the x or the horizontal axis. An example to show this is if we had a cart that would launch a ball straight up and this cart was stationary, it would launch a ball, the ball would go up, and then it would fall right back down into the barrel. That's looking at motion going on in the y or the vertical axis. But here in this video, we can see that if we add motion in the x-axis and the cart is moving, this does not affect the travel of the ball in the y-axis. It still lands in the barrel. Bounces out a little bit at the end, but you get the idea that it goes up and falls back down right in the same spot that it left, similar to when the cart was stationary. To explain this, we could have an analogy of a scenario where the background is moving and the cart is staying in the same position. Background's moving like this, the ball's going to go up and fall back down just as it did in the first situation. And as long as we're moving at constant velocity, the background or the cart, you actually can't really tell the difference between the two. So both scenarios are going to act out the same way. And we can use this concept to look at X and Y components separately. Let's look at an example of a boat moving at an angle. If the boat is traveling in this direction, let's imagine that someone is viewing the boat's motion from a bridge over here, and someone is viewing the motion from the shore. I'm going to use red lines to show what each eye is going to see. So as the boat moves, we can see motion in the Y direction moving up, and in the X direction moving to the left or west. And each eye is going to see this motion. The eye on the bridge sees this motion, which is the north component, and then the eye on the shore sees this component, which is the west component. So this angled motion has both north and west components. And this idea of components was super useful in solving questions where we had vectors at angles and we had to put them together. If we take a look at this example where there's a boat on a river and the river isn't going directly in the x-axis, it's at an angle, and then the boat also not directly on the x-axis, it's at an angle. It might ask you for the overall final velocity of the boat. I'm going to quickly go through how we used to solve questions like this, as we will deal with angles and components in Physics 30. So first, some information about the question. Let's say that the boat is going at 6 meters per second and the water is going at 3 meters per second. We also need to know the angles. So let's say that the river is 20 degrees from the horizontal, or 20 degrees north of east, and that the boat is traveling at 30 degrees from north, 30 degrees from the y-axis. When we add these vectors head to tail, we can get the resulting vector from that. We add the two components head to tail and we get this resultant. The problem is those two components, it's hard to really figure out how long that red line is going to be because both the yellow and the blue are at angles. So now we use the idea that X doesn't affect Y, and we break these into their X and Y components, or their north, south, and their east, west components. So I'm going to draw a triangle here, a right angle triangle, and find the components of that 6 meters per second. You would use sine and cos to find these sides with trigonometry and find that the north component is 5.196 and the east component is 3 meters per second. We would do similar trigonometry for the vector for the water and find that the north component is 1.026 and the east component is 2.819. Now that we have these numbers, we can add the x's together and add the y's together because the x's do not affect the y's. X motion only affects X motion, Y motion only affects Y motion. So to make this a little bit clearer, I'm going to blur out the background here and create an X and Y chart. I'm going to start with those yellow numbers and put the X variables and the Y variables on their appropriate sides. So now I have X and Y. Then I'm going to take the X and Y components of the other vector and put them in their places as well. So now I can see that, for example, on the X, the yellow component was going 3 meters per second east, and then also for the blue component, or the water, was going 2.819 meters per second east. I add those two x directions and I add the two y directions and I get the totals for each category. Now I can use this to determine the final triangle shown here for the resulting vector. I'm going to put those components there, the x on the bottom and the y on the vertical one, and we're just going to use Pythagorean theorem to find the hypotenuse of a rounded number 8.5 meters per second and inverse tan to find the angle of 47 degrees. Another place where we could use these components is applying it to projectile motion. A projectile is anytime something is launched into the air and there's no longer any external force besides gravity going to be acting on it. So let's say that we have this cannon and it shoots a cannonball. The cannonball is going to shoot up horizontal, then it's going to start to curve due to gravity. Now, if we're looking at the x and y velocities here, it starts with a pretty high x velocity, let's say 8 meters per second. Because there's no forces going on in the x direction, nothing is pushing or slowing this down. If we ignore air resistance, like we mentioned last time, non-conservative forces, we're going to ignore that for this example. It's going to continue at 8 meters per second in the x direction that whole time. Again, you might think, well, gravity would slow it down. Gravity is acting in the y direction, and as we said before, x does not affect y. So let's look at the speeds in the y direction. Initially, if it was launched horizontally, it's just going to be going 0 meters per second, not up or down. It's completely flat, so no motion in the y direction. But then gravity will start to speed it up, so maybe after some time it speeds up to 1 meters per second, accelerates further due to gravity, 2 meters per second, and 3 meters per second. We see acceleration in y and constant velocity in x. So to finish off the video, let's do an example looking at not just a horizontal projectile, but an angled projectile. This question says that a snowboarder goes off a jump at 30 degrees above the horizontal at a speed of 8.5 meters per second. The snowboarder lands 4.0 meters below the lip of the jump. How far from the lip of the jump does the snowboarder land? So they're going to make an arc like that, and we're trying to figure out how far they are from where they left the jump. Okay, so this is a bit of a complex question. How we're going to start it is breaking that angled vector into its components. So I'm going to draw this angled arrow here showing the direction that the snowboarder launches, and I'm going to draw the x or horizontal and y vertical components. It did tell me that the angle was 30 degrees and that the snowboarder was traveling at 8.5 meters per second. So now I'm just going to use sine to solve for this vertical side. Sine 30 times 8.5 meters per second, and I get 4.25 meters per second. I'm going to use cos to solve for the adjacent side. So cos 30 times 8.5 meters per second, and I get 7.361 meters per second there. That's our first step. Now, next we have to consider that it's asking for how far from the lip of the jump does the snowboarder land. This is looking for a displacement in x. We said x does not affect y, so I need to look at what's going on in the x direction. So I'm going to put a label here for x, and we have to ask if there's acceleration or constant velocity. As we saw with the cannonball, if there's nothing forcing or putting a force on the person here in the x-axis, there should be constant velocity. Nothing's causing it to speed up or slow down, again, ignoring air resistance. And our formula for constant velocity is v is equal to d over t. Well, this looks simple. We just multiply by time. I'll take the velocity in x, 7.361, multiply by the time, but unfortunately, they didn't give us any information about time. So how we get time is we need to look at the y-axis. So let's write y over here and see what's going on in the y-axis. Well, in this case, there is a force and there is acceleration. There's gravitational force accelerating it down. So now we need to determine an equation that deals with acceleration. And how we do this is we list our variables of velocity initial, velocity final, acceleration, time, and displacement. So let's see what we know. Velocity initial, we know is the 4.25 meters per second. Velocity final, we don't know what that is because they're going to be falling below where they started. Acceleration, we know, is negative 9.81 meters per second squared. That's the acceleration of gravity. Time, we don't know. That's why we're over here in y. And displacement, we actually do know. We said it was 4 meters below where it left the lip of the jump. So I'm going to put 4.0 meters, but I'm going to put negative because that's what I put for the acceleration of gravity. I'm calling down negative, and I have to keep those signs consistent. So now what I need to do is I want to solve for time. There is an equation to solve for that, but it involves a quadratic. If you've taken math courses where you are comfortable with solving a quadratic, you can use the formula D is equal to VIT plus half AT squared. I'm not going to require you to use that, so we're going to solve for VF and then solve for T. I'm going to use the equation VF squared is equal to VI squared plus 2AT to solve for our velocity final. Again, these are just from your formula sheet, these formulas. The rearrangement, not too hard, just take the square root to get VF. Let's put in VI of 4.25 meters per second. Square that number. Plus 2 times negative 9.81 meters per second squared, getting a little small there. But now times by -4. That -4 becomes very important here so that we keep the signs correct. And then we take our square root, and I'm getting a number for VF to be 9.8256. Let's keep lots of digits. 9.8256. Now here we have to consider if that is going to be plus or minus. Your calculator gives a plus. When we take a square root, it could be a plus or a minus, since 2 times 2 is 4 and -2 times -2 is 4. So the square root of 4 is both positive and -2. So we can have either answer. In this case, we have to see which makes sense. And at the end, the person is going to be falling downwards. So we have to choose the negative in that their velocity is going down. Okay, that's VF. Now that we do know VF, which is good, we can solve for T. I think the easiest formula would be A is equal to VF minus VI over T. Again, from your formula sheet, we'll just rearrange it by switching A and T out. T is equal to VF, negative 9.8256, minus our VI of 4.25, and we're going to divide by the acceleration, negative 9.81 meters per second squared, and I'm getting a time of 1.434. So a fair amount of work for this, but we're almost done. Hopefully it's a little bit familiar from previous courses, but if not, hopefully it's recapping it and making sense. So now we're going to plug that time value back in here, which is where we started and the reason why we needed time. So we multiply that 1.434 seconds by the velocity in x, and I get a number of 10.561. Let's round that to 11 meters based off our 2 significant digits. And that's how we'd solve for a projectile question. Okay, so I hope those topics were making sense. I know it was pretty fast, but hopefully they were familiar from previous courses. These ideas of components and also projectiles will continue on into Physics 30. So it's good that we just review those before we start. But you can let me know if you have any questions, try the practice questions, and I'll see you in the next video.